Okay, good morning. Today we're going to review for the second exam, which I'm going to post on Blackboard on Thursday, and it will be due for my Monday, Wednesday class. Will be due Monday of next week. My Tuesday, Thursday, it'll be due Tuesday of next week. Okay, so what is this going to cover? So exam 2. It's going to cover set theory, functions, and algorithms. Okay, so from Rosen, this would be sections, say 2, 3, and then 3, 1, 3, 2, and 3, 3. Okay. So let's just go ahead and look at some problems that will be similar to the ones that will be on the exam. I'll start with some set problems, and then we'll get to functions, and then finally algorithms. So suppose maybe, I don't know, maybe show that A set difference B is equal to A intersect B complement. Okay, so this is example, so maybe we could start playing around with it and say, okay, maybe just look at the definition and see if we can get from one side to the other. It's a set of x such that x is in A and x is not in B. This is a fairly simple one because here, so if x is not in B, then x is in B complement. And you could just write over here, it's like maybe since x not in B implies x is in B complement. Okay, but this here, this is the definition of saying that x is in A intersect B, or intersect B complement, I'm sorry. And that'd be it for that. Okay. So that was pretty simple. So I would imagine that one question will have parts like A, B, and C, and D, and they're just examples of showing that some set equation is satisfied, or some subset equation is satisfied. So maybe I'll look at a subset. So show maybe A set difference B set difference C is a subset of A set difference C. I think that's a problem. Yeah. Okay, so again, we talked about this quite a bit when we were going over set theory. To show that something is a subset of another, you take an arbitrary element in this one, and then show that that element has to also be in this other set. And this is this element-wise argument that I mentioned. Okay? So maybe say, so let x be in this set here. Okay, so if x is in this set, then by definition it's going to be, so I would say, then by definition, x is in this set here, and x is not in C. Right, that's the definition of the set difference, right? And again, you're going to want to have like a note card next to you with all the definitions of the basic set operations. So just recall that this set here is the set of all x, such that x is in the first set, and x is not in the second set. So that's where the second sentence here pops up. Okay. So then x is in A minus B. So in particular, what we can say from this part here, we can say since x is in A set difference B, x is in A and x is not in B. Okay, so in particular, x is in A, right? And then also we know that x is not in C. So then we're almost done. So in particular, x is in A and x is not in C. Okay, so then maybe like hence or therefore or something like that. So hence x is in A minus C. Because that's the definition of A minus C, or A set difference C, right? Just recall that A set difference C is the set of all x such that x is in A and x is not in C. So since x is in A and x is not in C, then that, I guess you might want to say a definition. Okay. And that's the end of the proof. Okay. So again, to show that a given set is a subset of another set, you pick something in the first one and show that it must be in the other one. So I guess like it's been a few weeks, so just recall the definition that A is a subset of some set B whenever for all x is in A implies x is in B. Whenever that's a topology. So the idea is to pick something here and then show that it must be in the other side. So here we picked an element there and we saw that it must be in the other side. So it satisfies the definition of being a subset, and we're done. End of proof. Okay. All right. So that's kind of the proof flavors that you'll see, like the types of proofs that you'll see. So then also, there's another type of problem that I mentioned in lecture that I always like to put on the exam. So let's see if I can pick a good one. Say something like, so let A sub I be the set 0 to I. So the open interval 0 to I. So in using set notation, this would be the set of all x such that 0 is less than x, which is less than I. Okay. And then the problem would be find the infinite intersection, or I'll start with the union actually. If I is equal 1 to infinity, base of I, and the infinite intersection, I is equal 1 to infinity, a base of I. So I like putting these problems on the exam because it makes you kind of really think about the set structure and what's happening with unions. So, okay, so what does the union look like? So maybe like this would be like part A of the question. Okay, so what does that equal? That's equal to A1, union A2, union A3, union dot dot dot, off to infinity. It's infinite union. But what is A1? So A1 is the open interval 0 to 1. You plug in, just put a 1 there, put a 1 there. And what is A2? It's the open interval from 0 to 2. What's A3? It's the open interval 0 to 3. You keep on going. So what does this union end up becoming? Well, you can draw a picture to kind of help yourself with this. So let's look at the number line. So here's 0, 1, 2, 3, so forth and so on. So where is A1? So A1 is all of those numbers there. That's A1. What's A2? Well, A2 is like the open interval from there to there. This would be like A2. So it's all of those numbers. Right? I don't know if you can see that, but it's a 2. And so what's A3? Well, A3 is the open interval from 0 to 3. So I would just overlap it, but I want to distinct them, distinct from each other. And you just keep on going. So if you take the union of A1 and A2, this union with that, the union is a collection of elements that are common to both sets, that are contained in the sets. So it's just, the union of A1 and A2 is just all of that. So that's going to be the union of A1 and A2. So A1 is right there, A2 is all of that. So if you take the union, A1 is a subset of A2. When you take the union, then it's just the original set. In fact, it's probably important to note, I claim that if A is a subset of B, then A union B is equal to B. Right. Is that claim true? Right? Because it is true, but you should be able to argue why you can do that. So I would say on your own, prove this. But it is true. So notice that A1 is a subset of A2. So when you union this with that, it's just this one. And then A2 is a subset of this, and you union that with that, it's just that one, A3. So if you keep on doing this union forever, you're gonna have that. So this would be equal to all positive real numbers. Okay. Okay, so what about the intersection? So we want to look at the intersection from I equal 1 to infinity of I. Well, this is A1 intersect A2 intersect A3. So this is 0, 1 intersect 0, 2 intersect 0, 3 intersect off forever. So if we look at our picture here, A1 intersects A2 is just A1, right? And then A1 intersect A2 intersect A3 is still just A1. So this is just going to be 0, 1. And that follows from the claim that if A is a subset of B, then A intersect B is just equal to A. And so I would definitely suggest that you prove this. Okay. And by the way, how do you prove set equalities like this? Well, you can string together a list of set identities in some cases. Here, it's not so clear that you can do that. So you would probably assume the hypothesis and then pick an element over there and then show that it must be there. And then pick an element there and show that it must be there. Does that make any sense? Like, be honest in the comments right now in the chat. Do any of you think that you could prove either one of these claims? If you tried for a little bit, anyone? You can say no, by the way. That'll help me decide whether or not I should show you how to do that.
No.
Okay.
No.
All right. Well, let's prove it. Okay, so I guess like proposition. So if A is a subset of B, then so A union B is equal to B, and then part B, A intersect B is equal to A. Okay. All right, so I guess I'll prove the first one. So proof of part A. So the idea is to say, okay, what does it mean for two sets to be equal? You have to have that like on hand in order to prove these types of things. So A is equal to B. The two sets are equal whenever X is in A if and only if X is in B, if that's a tautology. Okay. So in order to show that these sets equal, if I pick an X over here, it better be over there. If I pick an X over there, it better be over there. That's that biconditional operator from logic, right? This is only true when, if that's true, that's true, and that's true, that's true, and that's false, that's false, that's false, that's false. Okay, so I'm just going to say, okay, suppose, or maybe, suppose X, oh no, sorry, I need to suppose the hypothesis here. Suppose A is a subset of B. Okay. So we're assuming the hypothesis. All right, so next we're going to say let's suppose A is a subset of B. Okay. Next, maybe say let X be an element of A union B. All right, so I'm picking something on this side. I want to show that it's over there. Okay. Okay. All right. So now we're going to use our hypothesis here. A is a subset of B, so we can say okay. We can say it would be since A is a subset of B, if X is in A, then X must be in B. Okay, that's the definition of being a subset. Okay. Okay. And then we can say, so X so let's say, what do you say? Okay, so since A is a subset of B, if X is in A, then X is B. Well, maybe I skipped a step. I should say, so next let that being that, so then I should use the definition of this here. So then that definition. X is in A or X is in B. Okay, and our goal, again, we're going to pick something over here and then show that it's also in there, right? So X is in A or X is in B. Okay. If X is not in B, no, sorry. I can say if X is in A, then since A is a subset of B, X is also in B. So we say, hence, something like A union B is a subset of B. Okay. So we picked an arbitrary element in A union B. So by definition, X is in A or X is in B. If X is in B, fine, whatever. Um, uh, that's not the case you have to worry about. You have to worry about if X is in A. Okay? So then, if X is in A, then since A is a subset of B, X is also in B. In either cases, anything inside of the union must also be in B. So the union, this A union B is a subset of B. And then now we have to show that B is a subset of A union B. So we pick something over here and then show that it must be an element over there. So next, let X be an element of B. Then clearly X is an element of A, or X is an element of B. And so X is an element of A union B. So that part was easy. B is a subset of A union B. And now we've shown that A union B is a subset of B, and B is a subset of A union B, so that means they must be equal. So I'll just clarify that with one last sentence. So since A union B is a subset of B, and B is a subset of A union B, A union B must equal B. Or something like that. So I guess like the only tricky part was to show this part right here. B is always a subset of this union, but the union is not necessarily a subset of B. It just happens to be the case that since this holds, that's going to hold. Okay, so let's prove the other thing. Actually, I'm looking at this and it's kind of messy. I don't like it, so we'll fix it, which I know is going to seem annoying, but I think it might be clearer if I write this proof a different way. So I'm going to start by saying maybe clearly B is a subset of A union B. Now, is that clear to people that this is a subset of the union? Type yes or no, someone.
Yes.
Right, because like if you pick something in B, obviously it's going to satisfy being in A or in B. So
Right.
Yes.
Okay. Okay, good. All right. So now, so next, so okay. All right. So I'm trying to like piece this together in the nicest way possible. So let's let A be a subset of B, and then I'll write clearly B is a subset of the union. And okay, so in order to prove, so in order So, so it suffices to show that A union B is a subset of B in order to prove the equation, right? This equation. Right, so recall that so if A is a subset of B and B is a subset of A, then A is equal to B. It's a biconditional actually. That's the definition of being equal in another way. So since that is a subset of that, in order to prove that, we just need to show that that is a subset of that. Okay? So that's all that this sentence says. So it suffices to show that in order to prove the equation. Because we already have one side kind of like clearly, right? Okay. So say let X be an element of A union B. And suppose by contradiction, so again, we're supposing the opposite. That X is not in B. Or, again, I'm just trying to write this as clear as possible for your notes. And so, maybe like that, and by definition, X is in A, or X is in B. Okay? So one of these must be true, right? In order for that X to be in the union. And our goal is to show that X must be in B, right? Taking X in there, you want to show that it's in there. That's the whole point of doing that. So if X is in there, then X is in A or X is in B. Now, I'm going to suppose by contradiction it's not in B. So if X is not in B, then in order for this or to be true, X must be in A. And then maybe something like, however, since A is a subset of B, if X is in A, then X must be in B. Right? So X must be in B. Right? If it weren't, then we get that it also it must be. So how can it be? How can those both hold? So that's the I should maybe just write out contradiction, like a contradiction. Hence, X is in B. Follows that since you picked an arbitrary element in the union and it had to be in B, it follows that A to B is a subset of B. So we've shown that B is a subset of A and B, that's clear. And then because A is a subset of B, we've shown this must also be true. Because they're both subsets of each other, we have hence A and B is equal to B. Okay, so that's probably, again, I'm trying to make it as clear as possible to the reader. That's the whole goal of proof writing, is to you write down a proof and then it doesn't look so good, it's not as clear, it might confuse someone, try writing it again, until you finally decide that if people read it, they'll be able to understand it. Okay, so, okay. Okay, and the proof for part B would be very similar. Right, so, like, note here clearly A intersect B is a subset of A. The hard part is then to show that A is also a subset of A intersect B under this condition. Okay. So I'll leave that part for you to kind of try on your own and mimic what I did in part A. Okay. So there's that. Maybe I think that's enough on sets. We move to functions now. So let's say let f be a real value function with f of x greater than 0 for all x in R. And says show f of x is strictly increasing if and only if g of x equals to 1 over f of x is strictly decreasing. Okay. All right, so let's look at the proof of this. So notice that there's two statements here because it's a bi-conditional statement, right? We have that. So if f of x is strictly increasing, then g of x is strictly decreasing, and then the converse of that is if g of x is strictly decreasing, then f of x is strictly increasing. And that's because there's a bi-conditional if and only if right here, which means that there's two things to prove. Okay, so I guess so that's f map R to R. F being positive, right? Okay. Okay. Suppose first maybe let that, and then R, and let G of X equal 1 over F of X. Okay, so first we're going to suppose F is strictly increasing, then and show that that implies G of X is strictly decreasing, and then conversely, we're going to show that G of X strictly decreasing implies that F of X is strictly increasing. So suppose first F of X is strictly increasing. Okay, so supposing we have an increasing function. Again, you should have like a cheat sheet or something with all the definitions that we've gone over since the last exam. So what does it mean to be strictly increasing? Maybe I'll write that up here. So F of X strictly increasing means that if X is less than Y, then F of X is less than F of Y. That's the definition of being strictly increasing. Okay. Next we can say let X and Y be real numbers with X strictly less than Y. Okay. Then maybe since F of X is strictly increasing, we know that F of X is less than F of Y. Okay. Also, we know that F of X, so F is, actually the X is kind of confusing here, I guess, because we're using it in different contexts. So maybe just take A and B with A less than B. Okay. So, but if this is true, then this means that, there's like a double arrow here. This means that 1 over F of B is strictly less than 1 over F of A, right? Just divide both sides by F of A, divide both sides by F of B, and you get that right there. But this is the same thing as saying G of B is strictly less than G of A. So if A is less than B, then G of B is strictly less than G of A, which means that G is strictly decreasing. That means G of X is strictly decreasing. So we've shown that if f of x is strictly increasing, then g of x must be strictly decreasing. Okay. But we're not done. We've only proven this direction. If this, then that. Okay? It remains to show that if that, then that. The other direction. Okay. So if I had more room, I would start right here. Conversely, suppose that g of x is strictly decreasing. So I would continue writing down here, but I ran out of room, so I'm just going to erase and start up here. So conversely, suppose g of x is strictly decreasing. And it's basically a similar type of argument now. So let A and B be real numbers with A less than B. Okay, so then since g of x is strictly decreasing, I know that g of b is strictly less than g of a. Okay, yeah, that's the definition of being strictly decreasing. But g of b is equal to 1 over f of b. And g of a is equal to 1 over f of a. Now again, since f of x is positive for all values, we can multiply both sides of this by f of a and f of b. And the inequality is not going to flip. So then this means that f of a is strictly less than f of b. And I probably should have written on the previous equations along with this one that we call f of x is greater than 0 for all x. Because that just makes sure that the reader knows that the inequality is not going to flip. There's no negative that you're multiplying by. So a is less than b implies that f of a is less than f of b. So hence f of x is strictly increasing. So now we've proven this direction. So we proved one direction, prove the converse, and we're done. Okay. Okay. So that's an example of an argumented proofs involving strictly increasing, strictly decreasing. Okay, so let's maybe look at no, I think that should be it for sets and functions. You're going to want to review the YouTube videos that I've made on sets and functions as well. But as far as a test review goes, those types of problems seem kind of similar to what I would put on there for sets and functions. There's that. And I think that'll be it for today's lecture. And then next time, I'm going to review complexity.
Real quick, I have two questions from the practice problems that you assigned. I was wondering if you could work two of them for me, since I am having trouble with them.
Okay.
There's just two. The first one is number 10 from 3.1, and the second one is number 20 from 3.2.
Okay, let me take a moment to look at these.
Okay, thank you.
Let's see. Okay. So this is 10 from 3.1. Okay, it says devise an algorithm to compute x to the power n where x is some real number and n is an integer. So n can be positive or negative. Okay. So basically, it wants you to write out pseudocode to do this. Okay. So I guess our input is going to be x, which is a real number, and n, which is an integer. Okay. And then our output is just going to be x to the power of n. Okay. So what we can say is that, okay, so I'm just going to say, maybe said, maybe s equals to 1, and maybe say maybe a for loop. So I equals 1 to n. I'm going to say s is equal to s times x. Okay, so what that's going to do is going to cut it 1, right? So 1 times x, that's my new s. And then if I included 2, would be x times x right here, right? I is equal to 3, the x times x, which is s times x. And if you keep on doing this, this should result in x to the power of n. Now, then you have to have an if statement. So if, so here, I want to take the absolute value of n, because if n was negative, then this for loop wouldn't make any sense. So from I is equal to 1 to absolute value, then I want to multiply x by x by x by x by x by x.
Okay.
So then you can say if n is greater than 0, return s. If n is less than 0, return 1 over x.
Okay.
Does that make any sense?
Yeah. Yeah. Thank you. Thank you so much.
So maybe like maybe not if maybe like else.
Professor?
I do want to say that maybe the n is not equal to 0 here, but I could fix that if I put an if at the very beginning. But yeah, someone have a comment?
Yes. Just quick question. Where it says s equals s times x, what does the x stand for? It's a real number, but
Yeah, like suppose you wanted to like suppose we wanted to actually like run this algorithm, right? But suppose we want to know what like 4 cubed is, right? Suppose you wanted to write an algorithm to do that. This should work, right? So here, x is 4 and n is 3. So it's just raising x to the power of 3. They're raising 4 to the power of 3. So the s is equal to 1, and then for I equals 1, 2, 3, s is going to equal s times x. Well, so when I is equal to 1, right, we're going to have s is equal to 1 times 4, which is just 4. Then we increment I, so then when I is equal to 2, s is going to be equal to s, which is currently 4, times 4, which is equal to 16. And then
okay.
finally, when I is equal to 3, s is equal to s times 4, right?
Cool. Cool. Okay.
Yes.
Is that
Yeah, that makes sense.
It makes sense. I see it now. I was just curious what the x was, but never mind.
so then what would this be? So it's 40 plus 64. And then we break out, so then currently s is equal to 64, which is 4 cubed, right? Well, yeah. So then n is greater than 0, so we're just going to return 64. Now, I did have to specify that n is not equal to 0, but we could fix that with an if statement over here. So I'm going to quickly write that down. I don't like that non-zero part right there. Yeah, that's kind of annoying. So if n is equal to 0, return 1, right? Else, then we write down the algorithms like s is equal to 1, and for I equals 1 to n, the absolute value then, s is equal to s times x. Right there.
Cool. Okay.
And in here you would have your if statement. So if n greater than 0, return s. And then else, return 1 over s.
Okay. Cool.
Okay.
Thank you. Thank you so much.
And then what was the other problem?
The
20?
other problem was number 20 from 3.2.
Okay. Okay. So let's get that real quick. Okay, so it says determine whether each of the functions log of n plus 1 and log of n squared plus 1 is big O of log n. Okay, so I'm gonna look at both of them. So absolute value of log of n plus 1. And so this is going to be positive whenever n is greater than or equal to 0, because log of 1 is 0, and then anything that's increasing. So I can drop the absolute values when n is greater than 0. Okay, so here, what can I say? I can say maybe something about the inside here. So when n is greater than 1, I can get rid of that 1 right there. So this is less than or equal to log of n plus n when n is greater than 1. I just replace that 1 by the n, and this is an increasing function, so it just gets bigger.
Okay.
And that's equal to log 2n, right?
Right.
However, we can do this trick again. When n is greater than 2, right? I can replace that 2 by n.
Okay.
Because so, like if n was 3, then 3 times n would be bigger than 2 times n. And it is 4, so okay. So if I replace that 2 by n, I get that, which is equal to log of n squared, right?
Right.
But then we have that logarithm rule where the exponents can come to be coefficients. It says log n squared, by the way. Sorry about the word. Then this is equal to 2 times log n. And again, we have to make sure that n is greater than 2.
Right. Okay.
Both sides. And this is equal to, we're basically done. It's 2 times the absolute value of log n.
Right. Okay.
So then our witnesses would be, so we'd say, take C equal to 2 and K equal to 2. That's our constant, that's our K there. So
Okay.
yes, this one it can be big O log.
Okay.
And I think the same argument is going to work for this one as well.
Okay.
Because we can replace that, like, I'm running out of time, but let me just quickly try.
Oh, sorry. Thank you so much.
Yeah, this helps. I enjoy it when students actually ask me questions, because then I can get a sense of where you're at.
Right.
Okay, so let's look at this other one. That's a value log n squared plus 1. Again, the same trick. Whenever n is greater than 0, we can drop the absolute values. Like that. And then when n is greater than 1, n squared is greater than 1. So n s log is an increasing function. We can write, so again, this is n equals to 0, and here, we have n squared plus n squared, then n is greater than 1. And then this is equal to log 2 n squared. But then when n is greater than root 2, when n is greater than root 2, then n squared is greater than 2.
Okay. Yeah.
So then this would be less than or equal to log n squared times n squared. But that's equal to log of n to the power of 4, which is equal to 4 times log of n. That's equal to 4 times the absolute value of log n. And again, we have to make sure that n is greater than root 2.
Okay. Okay, cool. Thank you so much.
Mhm. Okay, so please go. So I guess on Blackboard, I'll post suggested problems again from those sections. And if you can, please take a look at them before next class and ask me questions about those. That'll help you. And honestly, when I write the exams, I look through Rosen and I just pick random problems in the sections.
Sweet.
So, all right. Well, I hope everyone is staying safe. And I will see you next time.
Thank you so much.
Have a good day.
Bye.